November 9th. We got a bunch of definitions for you to write down in your notes here today. But let's start with this little comic. We have this little I saying to pi, be rational, and he's saying get real. So I'm going to put in a question here for you to say whether or not you understand this, yes or no. And hopefully by the end of this lecture, you will be able to get why this is funny. All right. Objective for today is to be able to express our answers to quadratic equations using imaginary numbers. Why are we doing this? So we can answer questions that were previously unanswerable. All right, so I'm going to kind of build up our understanding of number types all the way up to complex numbers. But first, we need to address the kind of fundamental two different ways to understand numbers. So you got Platonism and nominalism. And these two theories can be boiled down to either numbers are real, and every time we are writing numbers, we are invoking some perfect idea of these numbers, or numbers are not real. They are just simply a tool, but they are not grounded in anything. And there is no correct answer here. You can understand all of math with either of these ideals. I'm going to understand this more from a nominalist perspective today. Here's a quote I really like from Eugene Wigner in his essay, The Unreasonable Effectiveness of Mathematics in Natural Sciences. He says, the enormous usefulness of mathematics in the natural sciences is something bordering on the mysterious, and there's no rational explanation of it. So I think this kind of helps resolve the conflict a little bit, like, numbers are real, numbers are not real. Well, it doesn't really matter because they are enormously useful regardless. All right, I'm going to give you another question to think about here. Why did we invent numbers? Imagine yourself as a cave person starting to form societies. Why would you want numbers? And you can write as much as you want for this one. All right, so it's very likely the very first numbers were the counting numbers. To keep track of this, I want you to start a whole new page, and in the very middle of that page, put a very small circle and write counting numbers in it, and put this symbol. It's a double struck N, and that N is because we also sometimes call these our natural numbers. But these were probably the first numbers that we started using. You can have 3 friends. A field can have 6 cows. You start at 1 and you just keep going up. All right, so what does a 2 actually mean? Well, it's any set containing 2 objects. So 2 birds, 2 trees, 2 cows, 2 apples, 2 POC, and 2 chains, making 2 wrappers. You can see this is actually already a big leap in our cognitive ability because it requires that we be able to identify similarities and group things. And then also represent them with abstract words and symbols. We probably didn't use this symbol for a 2 first, though. We probably started with a counting system like this, Roman numerals, where we are representing objects with just lines. So this still, is a pretty big accomplishment. It's still representing something in an abstract way. But, it's really straightforward, And then you can maybe group it up with a diagonal line, make that a 5. If you're doing, these are actually just tallies. They're not even Roman numerals. Roman numerals are where you start using things like an X to represent 10 or a V to represent 5. But this system is missing something. So imagine you're using your early counting system to keep track of your cows, and then one day you walk out and you see this. All of your cows have run away. So what are you going to write down for how many cows were in your field that day? Well, if you only use tallies as your number system, then you're just going to have to leave it blank. But, then the next day, do you fill in that blank? How do we show that this day had no cows? Well, so we've got harder problems, so we need to expand our number types. So the next layer of your bullseye write whole numbers in it and put a double struck W in there, which has got 2 extra lines. Draw it more like that. This is a bad one. So this is a whole new number system. You're counting numbers plus 0, and it makes the whole numbers. All right, and 0 is a big achievement because now we can start representing place value, and the number 102 is different than the number 12 now, because we can represent the place value of tens, put a 0 there, meaning we got 0 tens, and these are different numbers. But it requires we think even more abstractly about numbers, because we can't count to 0. It's just is the absence of something. Anyway, how many cows do we have if we start with 1, but then sell 2? I'm going to embed another question here for you to actually answer that one. Do you think we have no cows? Do you think we have -1 cows? Well, I think the correct answer is actually -1 cows, in that you can have -1 cows. As our agrarian societies were getting bigger, we started trading, and it was really important to have negative numbers in order to do trade, because then you could go into debt. You would owe somebody a cow in the spring, but they could give you grain and food in the fall. And as soon as you got a new cow, it would go away. And so that's how you could tell that you really did have -1 cow. But this expands on our number system. We're now in the 3rd ring of our bullseye with the integers. So we add in the negatives to create the integers. All right. So notice, 0 and positive numbers, they still all count as integers. We added the negatives to the positives to create the integers. So all of these are integers. Okay. Now, next question for you. How could an orange inspire fractions? Imagine you're trading, and what you brought to the market that day was oranges. Why might you need fractions? All right. So, if your orange is really valuable, you might segment it into pieces to trade off for grain. Well, now we need a new way to represent parts of a whole, and that is our fractions. So when you add in the fractions to our integers, you get the rational numbers. And they get a symbol that looks like this. It's a double struck Q. Yeah, when it imports this file, it sometimes changes these symbols, but it's a Q that looks like this. And any decimal that terminates can be considered a rational number, because you can just move the decimal all the way to the end, put it over, a 1 with that many zeros, and turn it into a fraction. So any number that can be reached by dividing 2 integers is a rational number. All right. And with rational numbers, we had pretty much all the numbers we needed for a long time, until a bunch of Greeks started doing a lot of geometry, and they wanted to answer questions about triangles, like what is the shortest distance from A to B? This distance right here. Well, they came up with this really great theorem called the Pythagorean theorem. They proved it several different ways that showed that this distance here equals the square root of these 2 distances squared and added together. In other words, a squared plus b squared equals c squared. Well, then when they went to solve this, they realized that this number here cannot be represented as a fraction. And you could even prove that it can't be represented as a fraction. But it still is definitely a number. I mean, it's this distance here. It's just not a rational number. And so there's a lot of arguments about this, but then eventually they just decided to think of numbers even more abstractly, expand the number system once again, and they called numbers like the square root of 2 and pi irrational numbers. And here we've got this joke from Big Bang Theory: you must be the square root of 2 because I feel irrational around you. That will hopefully remind you that the square root of 2 is irrational. But once we add the irrationals to the rationals, we get our real numbers. The next layer out on your bullseye is the real numbers, which includes rationals, but it also now includes irrationals. So irrationals should go out here. and inside here were the rationals, which included, integers, whole numbers, counting numbers. The real numbers, this is actually a symbol we use a lot. It's the double struct R. Looks kind of like that. And then surely we must be done. But much later on, we started investigating polynomial equations a lot more and trying to answer questions like this. Where does the parabola cross the x-axis? Well, not really anywhere. And this is sort of like the situation of walking out into your field and seeing no cows and trying to decide, do I have no solution or do I have 0 cows? Well, we can say that this either doesn't cross or that it does cross, but it crosses somewhere off of this plane into an imaginary plane. So is this number on the number line, the square root of -1? No, it's not on the number line, because the square root of -1, there is no number squared that when there's no number that when you square it you get a -1. But we'll just think about numbers a little bit more abstractly here, and we'll put this number off of our number line. The first person to really start thinking about doing math this way was this guy, Raphael Bombelli, in the 1500s, who decided that he wanted there to be a solution to those quadratics we couldn't previously solve. So, how do we define imaginary numbers? Well, first, the square root of -1 equals I. This is something you need to memorize. And then, if this is true, we could square both sides and get that I squared equals -1. So, can we write the square root of -5 with I? Here's how we would do it. You take the square root of -5, you split it into the square root of -1 times 5, you distribute your square root, and then the square root of -1 by this definition here equals I. So this would be I root 5. But typically, I actually goes at the end. So we would go root 5 I. All right. Here's another comic for you to help you learn that this type of number is called a complex number. So why can't we be together? It's complex. That's what the -1 is saying. So this is your next ring out on the bullseye. Once you add in the imaginary numbers, you achieve the complex numbers. So underneath complex is all the reals. But now we are including imaginary numbers. And what this is really accomplishing for us is it's letting our numbers be two-dimensional. They'll have a real part and an imaginary part. And that lets us do all sorts of cool math where we have a two-dimensional number versus a one-dimensional number. The number 8 is technically a complex number because it could be written as 8 plus 0i. So we can say it has an imaginary part, but it's just set to 0. And its symbol is the double struct C. All right, so a nominalist would say math is only as real as it is useful. So if we can't find a use for imaginary numbers, then we really shouldn't be talking about them. But here we have a slide from an electrical engineering class, and you can see I is appearing all over the place. So here doing electrical engineering, a useful thing to society. We need I to be able to do the math a lot quicker. All right, so do we understand this now? So pi is a irrational number, so I is saying be rational. I is imaginary, so pi is saying get real. Very funny. Okay, so that's as far as we'll go with this class, but just so you know, there are even higher orders of numbers. Here's a slide on them. And then there are things that we don't really even consider numbers, like infinity. And we can group these together as surreal numbers. So, our math really breaks down with numbers like infinity, but they still sort of work as numbers. So, like infinitesimals, the entire field of calculus is built on infinitesimals. Do they really fit within our number system? Not quite, but we just expand our number system out further, think about numbers more abstractly, and we can do some really useful math with it. Yep. And just one thing to know, this is a really cool proof in math, is that some infinities are bigger than other infinities. Really trippy thing to think about. And I'll just leave it at that. Okay. So, now that we know about imaginary numbers, let's solve this quadratic that we previously could not solve. I only have one variable, so I want to isolate it. I'm moving the 16 over. Taking the square root of both sides. And now before, I woot say, okay, taking the square root of a negative, this has no answer. But now I'm going to say, well, it does have an answer. I just need to think a little bit more abstractly about my math here. And split this negative 16 into a negative 1 and a 16. So I'm going to make it a 16 times a negative 1. Distribute my square root. And then the square root of 16 is plus or minus 4. So we get x equals plus or minus 4. The square root of negative 1 is I. So it does have an answer. It's just off of our number line into the complex plane. All right, can we solve this one by completing the square? Okay, so I'm going to rewrite this piece here as x plus 1 squared minus 1. Keep my plus 5. Right, this is x plus 1 squared plus 4 equals 0. Now move that 4 to the other side. X plus 1 squared equals negative 4. Take the square root, take the square root. X plus 1 equals the square root of negative 4. That is plus or minus 2i. And now we subtract 1, and so our final answer, x equals negative 1 plus or minus 2i. And there's our two answers. The negative 1 plus 2i and the negative 1 minus 2i. How would we graph this? This is how you would do this. You would go to negative 1 on your number line, and then you would jump off of your number line 2i units. So that shouldn't curve, but that's where these two numbers live. That is negative 1 plus 2i, and this is negative 1 minus 2i. All right. Solve by the quadratic formula. I haven't talked about the quadratic formula yet, but we're going to use it. So it's negative b plus or minus the square root of b squared minus 4ac all over 2a, where I fill in a equals 1, b equals negative 6, and c equals 18. So for this I would get 6 plus or minus the square root of 36 minus 4 times 1 times 18. It's going to be 40 plus... Why can't I do that in my head? 40 plus 32, 72, so minus 72 all over 2 equals 6 plus or minus the square root of negative 36 all over 2. Here we would stop, but we can go past the square root of negative 36. This is going to be 6 plus or minus 6i all over 2, which I could then split out. I can still do the division. I can still make this 3 plus or minus 3i. We're allowed to do that even with the I there. And there's our answer. All right. You can do operations with imaginary numbers, like 5i plus 2 times 3i minus 1. We can FOIL this. And the I sort of just acts as a variable. The one thing is when I do 5i times 3i, I get 15i squared. And we'll talk about that in a second, but the I squared can become something. When I do outside, I get minus 5i. Inside, I get plus 6i. Last, I get minus 2. All right, so here's the trick. I squared equals negative 1. So this 15i squared can become a negative 15. Minus 5i plus 6i minus 2. And then when we gather this, we want to send the term with I to the end. That's kind of slightly different. So negative 5 plus 6i is just going to be plus I. Slightly different than if it was a variable. We normally bring our variables to the front, but we do send I to the end. All right, so negative 17 plus I. And that's that for this video. So we'll end it here. No more questions, so just have a good rest of your day.